Hello, welcome to Basics of Finite Element Analysis. Today is the fourth lecture of this week, and what we will do is we will continue our discussion on the assembly process, and we will introduce a new term called a connectivity matrix, which is used to help us assemble complex assemblies on a computer. But before we discuss this, I wanted to make one specific point related to implementation of boundary conditions. In the last lecture or the lecture before that, we had seen that if we have a bar which is broken into 3 elements, then at the assembly level we get 4 equations, and the K matrix is of a 4 by 4 type. And then looking at the specifics of the problem, we had seen that u was specified as 0 at x equals 0, and at x is equal to L, external force was applied which was equal to Q naught. So, we had applied in that case, we had made u1 to be 0 in the first equation, and that was the enforcement of the essential boundary condition. And the second boundary condition which was specified was that force at x equals L is Q naught, and that is what we had applied here in the last equation. And at that point I had mentioned that we look at these assembled equations and we look at only those equations for which u is not known, and then we will only use those equations to solve for the unknown values of u's. But I should have additionally mentioned that when we look at these equations, those equations which are captured in this green box, we have eliminated basically one row from the whole system of equations, and we should also eliminate one column from the system of equations, so that our reduced K matrix is still of a square type. So, in this case we will eliminate the first column, because the first column is associated with u1, which is the boundary condition which we know. Okay. So, not only we should remove a certain number of rows, but an equal number of columns from the system of equations, so that we get an n by n K matrix, and using this method then we actually solve for unknown primary variables. So, this is something I wanted to mention, because I think I forgot it in that class, and you may be getting confused. So, just wanted to bring it to your notice. So, today what we are going to discuss is a matrix called connectivity matrix. Connectivity matrix. And in context of this, we will look at the multi-bar problem which we had analyzed in yesterday's lecture. So, the that problem was something like this. So, I have 2 parallel bars connected by a rigid plate, and then I have another bar at the middle which is rigidly fixed, and I had assigned some nodes. So, each bar is represented as one element. So, these numbers in red are the global node numbers. Okay. And we know how to straight away calculate the stiffness or the K matrix for each element using the methods we have discussed so often in last several lectures. What we are going to do is develop a matrix which will help us in the assembly process. So, and that matrix is known as connectivity matrix, and it is designated by this letter B. So, let us look at this. So, my connectivity matrix B equals, and first I will write down the matrix and then I will explain. It is 1, 3, 2, 3, 3, 4. Okay. The first row of this matrix represents global nodes of element 1. Okay. So, I should label my element, this is element number 1, this is element number 2, and this is element number 3. So, my first element is this guy, its first global node is 1, second global node is 3. So, it is like that. The second row represents global nodes of element number 2. So, that is 2 and 3. And the third row represents global nodes of element 3. Okay. So, this is what are the dimensions of this matrix? It is n times O, where n is the number of elements, and this is for line elements only, and O is, so it is O plus 1. O is the order of elements. So, if it is a linear element, then how many columns we are going to have? 2, because O is 1, 1 plus 1 is 2. If it is a quadratic element, then I will have 3 columns in this matrix. Okay. And the first row, first column, see this is C1, column 1. This corresponds to first local node number, right. So, for global element 1, first local node number is 1, which is what C1, and this second column represents second local node number. Okay. So, if there is a number in second column, that corresponds to the second node of the element. Now, this matrix serves as a very powerful tool to develop our overall K matrix. We will explain that. So, for this system, so first you compute the element level K matrices, all element level K matrices, and then you assemble them. How do you do that? So, your K11 for the first element is equal to global K11. Why? Because local node 1, this is local node, right? This is local node 1, this is local node 2. So, local node 1 corresponds to global node 1, and local node, and the second index is again 1, local. Actually, that will just create confusion. I will erase this. Okay. First vector corresponds to the first node, second vector corresponds to second node, third vector corresponds to third node, like so on and so forth. Okay. So, this first index is 1, and that is the local node number, which is this. Second index is again 1, which is again the local node number, and we know that local node 1 corresponds to global node 1. So, K11 prime, it goes into calculation of K11. Similarly, k1 to not prime, k1 to 1, which is the first element, it corresponds to k13, global k13. Why? Because local node 1 corresponds to global node 1, right. So, because the superscript is 1, only we are only looking at the first row, okay. Then local node 2 corresponds to global node 3, right. The superscript is 1, so I only look at the first row. In now the first subscript is 1, that corresponds to global node 1. The second subscript is 2, that corresponds to global node 3. I am only looking at the first row, okay. Now we also see that this number 3, it occurs in 3 places, which means that when we are calculating k33, it will have 3 components, okay. So what does this mean? Global node 3 corresponds to local node 2 in element 1, agreed. Again, global node 3 corresponds to local node 3 in element 2, 2 in element 2, and global node 3 corresponds to local node 1 in element 3. So I can say that k33 is equal to k221, this is coming from here, plus k222, this is coming from here, plus k113, this is coming from here, okay. So once you have defined the B matrix, you have actually captured the geometry of the overall system, how different elements are connected with each other. The B matrix helps computer understand how different elements are connected with each other, okay. And that understanding can be used to develop assembly level equations. You look at another term k24 for the global matrix, okay, k24 for the global matrix. So you see that this is global node 2, global node 2 is in the second element, okay, and global node 4 is in the third element, and this is the first node and this is the second node. So they are mutually disconnected, so this will be 0, okay. If they were in the same element, then you could have created something, but they are in different elements, so there is no connectivity between them, there is no physical connectivity, so that k24 is 0. So that was about connectivity matrix. Now we will make a couple of other important observations which are worthy of mention in context of our whole finite element method. So the first comment I wanted to make is that when we enforce the assembly conditions, we make sure that U is continuous. For a one dimensional problem and problem with one variable, U will be continuous. If it is, if two dependent unknowns are there, U and V, then we will assume U and V in such that U and V both are continuous, and so on and so forth. So U is continuous. So what this means is that if I have These are my different elements. My overall U could be like this, right. So, these variations between the elements between two nodes, they will be linear variations if the element was linear. They will be quadratic variations if the element was quadratic, and so on and so forth. So, that is why I have here made straight lines. Okay. But at the junction of nodes, if you calculate the value of U from left element or the right element, the values will be same, because we have mathematically enforced the continuity of U at junction points. So, U will be continuous. Second thing, du over dx need not be continuous. Okay. Because when we were doing the assembly process, we never said that d over dx is same. Okay. So, in this case, for a linear element, if you have a linear number of elements, then du over dx will be constant over one element. It may have a different constant value over another element. It will be like this for linear elements. For quadratic elements, it will be a linear, it will have a linear constant slope, but again there is no reason to think that at the boundaries it will be, the slope will be same and they will meet, okay, because the only thing we have ensured is that U is continuous. We have not mathematically imposed continuity of slopes. So, this distinction will be there. What does that mean? What it means is that when you solve, so du over dx in context of the bar problem is related to strain, right. Du over dx is strain. From strain I can calculate stress, which means that in the bar problem strains will jump across the nodes. On left side at the same location it may be 200 microstrains, on the other side it may be 300 microstrains. Okay. Same thing is also true for stresses. They will jump from one value to other values across the interfaces. Okay. So, strains will not be continuous, stresses will not be continuous, thermal gradients will not be continuous, heat fluxes will not be, not heat fluxes, thermal gradients will not be continuous, because thermal gradient is del T over del X. Okay. So, all these derivatives of fundamental quantities, they will not be continuous for second order boundary value problems, because we never ensured their continuity. Third, however, if we keep on increasing the number of elements larger and larger, these jumps between strains, this jump, they will reduce, they will never become 0. Mathematically they can never become 0, but they will keep on reducing. So, if you are looking for convergence of stress, you have to, if you are looking for convergence of displacement, because displacements are continuous, they converge faster. If you are looking for convergence of stress, you need even larger number of elements, you need even larger. Suppose you have convergence of U for 20,000 elements, that does not guarantee that your stresses will also be converged. For that maybe you have to go to 40,000 elements. So, stresses and strains converge slowly, slower compared to the primary variable. Okay. So, PVs converge faster relative to secondary variables. So, these are very important things to remember, because a lot of times when we do finite element analysis, maybe our U's have converged, but if what we are really interested in finding out the strain or stresses, then we have to look at those quantities to see whether they have really converged or not. Okay. If we are interested in convergence of U, or for instance a thermal problem, we are interested in find temperatures, then that is fine. But if we are interested in finding out how their gradients are changing, then we may have to do a more refined analysis with higher node numbers. Last point I wanted to make is that suppose you have this element xa to xb, and earlier we had said, so there is some distributed force and we know how to calculate the value of that force at xa and xp. We have seen that F1 and F2, right. Now suppose I have at this location a point force, and let us say that value is q e. So at some location I have a point force, I am pulling it, so that is q e. If the location of this q was exactly at the node, then I would have, when I did the assembly process, then q from this element and q from the next element, when they add up, this would have been equal to q, right. But if this force is somewhere in, point force is somewhere in the middle, then how do we distribute this force at two different locations? So that is what we will discuss. So what I can do is, so this is a point load, and I can represent this point load as again some q of x, because I know how to handle q. Q is the distributed force, right, q is distributed force. So I will express q, I will express q e, which is a point load, as a function of x. Let us say this coordinate is x naught. Okay. So I will say that it is equal to qx is equal to q naught, excuse me, it is q naught for the eth element. So it is equal to q naught times a direct delta function x at x naught. Okay. So what does that mean? That the value of this thing will be q naught only at x, right, at all other positions it will be 0. Now we know that if I have any function f of x, any function, it could be linear or non-linear, does not matter, and I multiply that by some direct delta function x minus x naught, and I integrate it over dx with respect to x, and I integrate it from infinity to whatever infinity, then this is nothing but f at x naught. Okay. So I use this principle to calculate the q. Okay. So what does this do? So what I do is that I say that f I for eth element, okay, is integral from xa to xb qx times direct delta function x minus x naught, and then I have to multiply it by weight function psi 1 e dx, right. I have to multiply. This is how I calculate by f vector. If there was a distributed force, then there would be another component, right, if it were, but I am just ignoring that, because suppose I I have to worry only about this, yeah. Q naught, yeah. So this is the thing, and this means that this value is Q naught psi times psi I. So this is for the ith shape function evaluated at x naught. Okay, which means that f1 corresponding to the first approximation function E is equal to Q naught at psi 1 at x naught, and f2E is equal to Q naught psi 2 at x naught. Now psi 1, so this is for a linear element. If it was a cubic element, then we change psi 1, psi 2, psi 3. Okay. Now we know that psi 1 equals xb minus x over he, and psi 2 is equal to x minus x a over he. So f1e equals Q naught times xb minus x naught divided by he, and f2e is equal to Q naught xb minus x minus xa divided by he, x naught. And when you add these two up, you will get the sum of these f1 and f2 will be Q naught. Okay. So if you have a point load in the middle of an element, you can do two things. Either you break that up element further so that there is a node at that point, or you use this mathematics to distribute that load accordingly between the two nodes. If it is a 3 noded element, then you have to use psi 1, psi 2, psi 3, so on and so forth. So this is the concluding part of this lecture, and we will continue our discussion tomorrow. Thank you.